Hello, welcome back, quantum friends, to Physics Computer Science 219A. We're going to have more fun with quantum entanglement today. And then finally, we'll be able to start talking about computation. That will be the goal for the next lecture. But I do want to say a little bit more about quantum entanglement before we move on. And in particular, this will be some further discussion about the things you can do with quantum entanglement. We've learned something about that already because we've discussed how with quantum entanglement shared between two or more parties, you can win a game with a higher success probability than you could if you didn't have entanglement shared by the parties. That's what Bell inequality violation is all about, which experiments have verified. Today, I want to talk about two related tasks, superdense coding and quantum teleportation. Quantum teleportation is a useful protocol. It's used as a subroutine in a number of tasks that we need to perform in quantum systems, in quantum networks. And it's also kind of cool and fun to talk about and think about. Superdense coding is very closely related, as we'll see. So let's talk about communication using a quantum channel, but where the goal is to communicate classically, just to send bits. It's kind of a waste, really, because with a quantum channel, you'd think we'd have more interesting things to do. But let's suppose the only channel we have around is a quantum channel. We can use it to send qubits. And let's suppose it's a noiseless quantum channel. That's the best kind. That means you can send quantum information over the channel with perfect fidelity. So let's say Alice and Bob are connected by such a channel. What it means is that Alice can prepare any quantum state of her choice for her system. Let's say it's a qubit, any state of the qubit that she pleases. She can send it over the channel to Bob, and Bob can do whatever he wants to do with it. He can measure it or store it in his quantum memory or whatever, but saying it's noiseless means that the state that Bob receives is exactly what Alice sent, just as though she had prepared it for him right in his own laboratory. Now, what we'd like to do, or what we'd like to talk about for the moment, is sending a bit or many bits using the quantum channel that's connecting Alice and Bob. Well, you can do that. To send a bit, you have to choose you have to choose a pair of perfectly distinguishable quantum states, mutually orthogonal states, and Alice can prepare one of those basis states or the other and send to Bob. And Bob, by prearrangement with Alice, knows to measure in the proper basis to distinguish the states perfectly. So they agree, if Alice is sending qubits to Bob, that Alice will always use the standard basis states, the computational basis state 0 or 1, and Bob knows how to make a measurement that perfectly distinguishes between the state 0 and 1. So every time Alice wants to send a bit to Bob, she prepares one of those two basis states, sends it through the channel, and then Bob measures it, and a bit is indeed conveyed from Alice to Bob that way. Now, let's say Alice can use the channel many times. She can send altogether n qubits. She could certainly convey n bits to Bob that way by sending the bits one at a time, the way I just described. A natural question is, can she do better than that? Is it possible with n uses of the channel for Alice to send more than n bits to Bob? It turns out the answer is no. I'm not going to prove that for you here today. There is a proof and discussion in one of the later chapters of our lecture notes, but we're not going to be covering that this term. But there is a theorem called Hellebose Theorem, and it has the consequence that we can't send more than n bits of classical information when we send n qubits. And that's not such an obvious fact, because if you think about sending some alphabet of quantum states, which Bob then tries to distinguish or tries to get some information from, Alice doesn't have to do what I say, what I just described, send one of two mutually orthogonal states. She could try something trickier. She could choose from an alphabet of many states for a single qubit. After all, she can prepare and send any pure state on the surface of the Bloch sphere, couldn't she? So she could choose from among a billion different signal states that she might send to Bob. The trouble is that Bob won't have a very easy time distinguishing all those states. And the content of Hellebose theorem is that because it's so hard to distinguish accurately non-orthogonal states, sending that much larger alphabet doesn't really do any good. It doesn't help Alice send more bits of information. Now, another tricky thing that Alice could try to do is prepare an entangled state of many qubits and then send all of those qubits through the channel one at a time. Now she's using entanglement across multiple uses of the channel, which sounds like a good strategy. But as long as they don't have any shared entanglement to begin with, this theorem says that, again, the best they can do when Alice sends n qubits to Bob is Bob receives n classical bits of information, if indeed the goal is to send classical information. But now let's suppose we change the rules a little bit. We'd like to know how empowering is entanglement shared by Alice and Bob, in particular for the task of classical communication. So we'll imagine now that Alice and Bob have had the foresight to prepare some entangled pairs of qubits, which they have at the ready when they need them. And now the question is, can they use that entanglement to communicate more efficiently? Let's say that they've had that entanglement in the bank for a long time, knowing they might use it someday. The quantum channel, although it's noiseless, or maybe because it's noiseless, it's extremely expensive to use. It costs $1 million every time you want to send a qubit from Alice to Bob. And now it so happens that today, Alice desperately needs to send 2 bits of classical information to Bob. His life is at stake, but she only has $1 million, so she can only afford to use the quantum channel once. But fortunately, they did put some entanglement in the bank some time ago, anticipating that they might need it someday. So how is it they're going to make use of that entanglement to communicate more efficiently? Well, we notice the following thing. Let's say that Alice and Bob have some time ago prepared a shared maximally entangled state of 2 qubits, 1 qubit in Alice's possession, 1 qubit in Bob's possession. Let's say the state phi plus, which is just the uniform superposition of 0 for Alice, 0 for Bob, and 1 for Alice, 1 for Bob. And we notice that if Alice alone, with no help from Bob, applies possible unitary transformations to her half of that entangled state, she can change the entangled state shared by Alice and Bob. Specifically, she could apply one of the Pauli operators, either the identity or the Pauli operator X, or the Pauli operator Y, or the Pauli operator Z. But what happens to that shared entangled state when she does those things? Well, Pauli operator X, that's just a bit flip. It changes Alice's 0 to 1 and her 1 to 0. So acting on this state phi plus, 0, 0 plus 1, 1 would become 1, 0 plus 0, 1. If she applies Y, then up to a phase, a vector of I, it performs that bit flip, changing 1 to 0 and 0 to 1, but also with a relative sign. It actually is going to change up to a phase, 0 to 1 and 1 to -0. So when y is applied by Alice to her qubit in the entangled pair, the state 5 plus becomes 1, 0, -0, 1. And she could instead apply the Pauli operator z, which changes the relative phase of the basis states 0 and 1. So when Alice applies z to her qubit, if the initial state is 5 plus, it becomes 0. Oh, there's a nasty typo. That should be 0, 0, -0, 1. No, it shouldn't. It should be 0, 0, -1, 1. Well, I'll have to fix that later. But anyway, let's notice that the 4 possible states that can be obtained in this way are mutually orthogonal states. I've given them names: phi plus, psi minus, and phi minus. They can be perfectly distinguished. It's easy to, if you have access to both of the qubits. If you have both qubits in your lab, these guys are mutually orthogonal. It's obvious that the states phi plus and phi minus are both orthogonal to psi plus and psi minus. They have different parity. The phi plus and phi minus, if it weren't for this typo, both have the property that if you take the OR, or you take the XOR of the 2 bits, you always get 0. It's either 0, 0, or 1, 1. You can certainly distinguish that from odd parity when it's 1, 0, or 0, 1. But also because of these relative phases, the 2 states with even parity are perfectly distinguishable. 0, 0 plus 1, 1 and 0, 0 minus 1, 1 are orthogonal. And likewise, 1, 0 plus 0, 1, 1, 0 minus 0, 1 are mutually orthogonal. So an orthogonal measurement can distinguish these 4 possibilities perfectly. Now, that we can distinguish 4 possibilities perfectly for 2 qubits is not a surprise. That's true of the standard basis too, right? We could have chosen basis states 0, 0, 0, 1, 1, 0, and 1, 1, and those are perfectly distinguishable as well. But what's special about these 4 is that they are all quote unquote Bell states. They are all maximally entangled states of our pair of qubits. So if you have both qubits in the lab, you can do a so-called Bell measurement projecting onto this Bell basis of phi plus, psi minus, and phi minus, and distinguish them perfectly. Now, we can think about it this way. If I prepare a phi plus, and Alice comes into the room, and she promises me that she's going to apply one of identity X, Y, or Z to one of the qubits, and she doesn't tell me which one. When I come back into the room, I can do this Bell measurement, and I can distinguish those 4 possibilities, those 4 possible operations that Alice could have applied perfectly. Okay, so now we can see what to do. Remember, Alice and Bob share a phi plus. They're in different cities. Alice is in Pasadena. Bob is in Waterloo when we last checked his whereabouts. And but Alice can apply one of identity X, Y, or Z that changes their shared entangled state to one of these 4 mutually orthogonal possibilities. Then she just sends her qubit to Bob. And when that qubit arrives with perfect fidelity, because the quantum channel is noiseless, in Bob's lab, he can perform the Bell measurement. He can distinguish 4 possibilities that way. He can tell which of 4 things Alice did. And in that way, Alice manages to send 2 classical bits of information to Bob, even though she sent just 1 qubit. So I've tried to indicate how that works here in a kind of space-time diagram. I guess because as a child, I learned general relativity. I like to think of time as running vertically upward sometimes. And so we imagine that somebody prepared phi plus. Maybe it was Charlie, you know, that guy in Denver. I guess it was Donald in Denver, wasn't it? At any rate, somebody prepared a phi plus, and gave one of the qubits to Alice and one of the qubits to Bob. That happened some time ago. And then Alice and Bob sat around for a while until the urgent need arose today for Alice to send those 2 classical bits to Bob. She took those 2 classical bits of information, she encoded them by applying one of the 4 operations, I, X, Y, and Z, to her half of that entangled state. She sent that qubit to Bob. Bob did the Bell measurement, and he was able to decipher those 2 classical bits perfectly. I like to write this as a kind of inequality, sometimes called a resource inequality. What an inequality like this is supposed to convey is that, I don't know how this kind of got misaligned, but at any rate, it's supposed to say that if you have the resources which are listed on the left, the greater than equal sign means that you can use those resources in some suitable protocol to simulate the resources on the right. And what my symbols mean here is the Q, arrow Q, means sending a qubit from one party to the other, in our case from Alice to Bob. The square bracket QQ means a shared entangled pair of qubits, sometimes called an E bit or entangled bit. It's just a Bell pair, a perfectly maximally entangled pair of qubits. And with that, we can simulate 2 bits of classical information. C, arrow C, means sending a bit from one party to the other, from Alice to Bob. And the SD is just my abbreviation for superdense. This is called superdense coding. That's maybe a little bit of an exaggeration. It's dense coding. That seems to be fair. We've managed to send 2 classical bits, which I called C bits here, just to make it easier to write, just using 1 qubit. That's what's dense about the coding. And in fact, we can't do better than that. Even if we have shared entanglement, if we're only allowed to consume this 1 E bit of entanglement and send 1 qubit from Alice to Bob, the most classical information we can send is 2 bits. Now, kind of an interesting thing about this communication is that the communication is perfectly encrypted. What I mean by that is, let's suppose there's some adversary, some eavesdropper who's dying to know what's so important that Alice has got to send Bob these two classical bits. And so she can't resist interfering with those qubits. Maybe she takes them into her lab and measures them before sending them on their way. Or I'm talking about the qubit that's going from Alice to Bob. Maybe Eve intercepts it and applies some operation to it. But that's not going to do her any good at all if her goal is to know what message Alice is sending to Bob, because that qubit that is in transit from Alice to Bob is half of a maximally entangled state. It's, in other words, a maximally mixed state. And no matter what the message is, it's a maximally mixed state. So the qubit that Eve intercepts, Eve the eavesdropper, is in exactly the same state no matter what the message is. And that's what I mean by perfect encryption. It doesn't reveal anything to the eavesdropper about the content of Alice's message. Now, there's a way of looking at this which makes it seem a little bit less sexy, which is, it might have been Alice herself who prepared the maximally entangled state. Maybe she did that yesterday, and she made the 5+ in her lab, and she held on to half of it, one of the qubits, and she sent the other half, the other qubit, to Bob. And now, today, she realizes she's got to send these 2 classical bits of information. And so today she decides that the entangled state of 2 qubits, she doesn't really want it to be 5+. She wanted it to be one of, she might want it to be one of these other 3 mutually orthogonal maximally entangled states. And so she takes these 2 C bits and she encodes it by performing the suitable operation. And then she sends the second qubit. So really, Alice is sending one of these 4 states, phi plus, psi minus, or phi minus in this scenario, because she sent both qubits to Bob. So from that point of view, Alice used 2 qubits of communication to send Bob 2 classical bits. Well, she could have done that just by using the standard basis both times. She could have sent either a 0 or 1 twice and accomplished that same task. So what's so great about superdense coding? Well, you see, it really is different than the scenario in which she sends the classical bits one at a time. For one thing, she sent that first qubit yesterday. Well, maybe she sent it 100 years ago. I don't know. But the point is, she sent it to Bob long before she knew what are the 2 classical bits that she wants to send to Bob today. So that's something they were able to do well in advance. And so when the crunch came and they had to communicate right away and only had $1 million and could only use the channel once, then it was still possible for Alice to send those 2 classical bits of information. It wasn't too late, even though she had sent one of the qubits a long time ago. Furthermore, in order to share the entangled state phi plus, it wasn't necessary for Alice to make phi plus in her lab and then send one of the qubits to Bob. It could have been the other way around. Bob could have made phi plus and sent one of the qubits to Alice. And so then it's quantum communication from Bob to Alice to establish that entangled pair. And then later, quantum communication from Alice to Bob. Well, that's a very different scenario than the classical one, because the communication was from Bob to Alice first and then from Alice to Bob. But somehow we managed to send 2 classical bits of information from Alice to Bob by that means. Or for that matter, it didn't have to be either Alice or Bob. As I had said previously, it could have been Donald, the master of entanglement in Denver, who made the entangled pair and sent one of the qubits from Alice to Bob. And again, as I emphasized already, what I described as encryption of the communication, in this case, when they use the entangled alphabet to send 2 bits of classical information, neither qubit by itself conveys any of the information. It's only the pair that does, because either qubit by itself is just in a maximally mixed state and doesn't tell us anything. That's in contrast to the scenario in which Alice just used the classical communication protocol twice, where she sent either a 0 or 1 the first time, or a 0 and a 1 the second time, in which case, of course, there is information in each use of the channel. So that's superdense coding. And now I want to talk about quantum teleportation, which is a related task. In a certain sense, it's kind of the dual of superdense coding. Whatever a dual is, that's a word we use a lot when we want to say 2 things are related to one another in some way. But what I mean by dual in this case is, I can say sort of concretely what I mean. If we look at the superdense coding protocol depicted over here on the left side of the slide, well, I've already described it to you. An entangled pair is created. It's distributed to Alice and Bob. They hold on to those entangled pairs for a while. Then one day Alice receives 2 classical bits of information that she wants to send along. And she performs one of 4 possible operations then on her half of the entangled pair, sends the qubit to Bob, and then Bob does Bell measurement over at his end, and he's able to decipher the 2 classical bits. So here, Alice is applying a unitary transformation. The communication from Alice to Bob is quantum communication, 1 qubit's worth. Bob does Bell measurement. And in the end, what the protocol achieves is 2 bits of classical communication from Alice to Bob. What does quantum teleportation do? Well, now the task is to send quantum information from Alice to Bob, okay? In fact, we can imagine a scenario where Alice and Bob, as usual, are in different cities. Alice in Pasadena, Bob in Waterloo, say, and a qubit has arrived in Alice's lab today, or maybe it was created in some experiment that Alice did in her lab. And it's of the utmost importance that that qubit be transferred to Bob's laboratory without being modified or damaged in any way. Maybe Alice has done some experiment which created a exotic state of this qubit encoded in such a way that she doesn't have the apparatus in her lab to measure that qubit, but Bob does. If it were only in Bob's lab, he'd be able to perform the measurement that they need to get the results of their experiment. So somehow Alice has got to get that qubit from her lab to Bob's lab, but it's very far away. And furthermore, that darn quantum channel, it's very unreliable. Some days it's working, today it's not. There's no quantum channel connecting Alice and Bob right now. And but they, their competitors are also doing the experiment, and they're going to be reporting their results tomorrow. So she better get that qubit over to Bob today, one way or another. In fact, she can do that. And here's what she does. Remember, they have entanglement, just like in Superdense coding. They have entanglement, which was prepared some time ago, which they share. Alice receives a qubit that maybe she created in her experiment. She's got to send it to Bob. She does Bell measurement on the qubit that she wants to send and her half of the entangled pair phi plus. When she does a Bell measurement, she's measuring in that basis, phi plus, phi minus, psi plus, and psi minus. There are 4 possible outcomes. She tells Bob what the measurement outcome is. That's 2 classical bits of information, enough to distinguish 4 possibilities. She sends those 2 classical bits to Bob, just calls him up on the phone. All they need to do is classical communication. Now, when Bob receives that information, he takes his half of the entangled state that he shares with Alice, which was created a long, long time ago, and he applies one of 4 possible operations: identity, polyoperator X, polyoperator Y, or polyoperator Z, to his half of the entangled pair. And in so doing, magically, he recovers in his lab a perfect copy of the qubit that Alice had in her lab. That's how quantum teleportation works. So you can see how similar it is to superdense coding, except it's kind of turned inside out. Here in superdense coding, we use quantum communication to send classical information that Alice has over to Bob. Alice performs a unitary, Bob does Bell measurement. Here we use classical communication, 2 bits worth, to send a qubit from Alice to Bob. Alice does Bell measurement, Bob does a unitary transformation, which depends on the outcome of Alice's measurement. So I can write that as a resource inequality. This time I'm abbreviating it TP for teleportation. And again, it means that the resources on the left are adequate for achieving the resources on the right. That is, with 2 bits of classical communication, C to C, from Alice to Bob, consuming 1 E-bit of shared entanglement, Bell paired, prepared by Alice and Bob or distributed to them some time ago. That's sufficient to realize 1 qubit's worth of communication from Alice to Bob. That's what the Q to Q means, okay? And that's what quantum teleportation tells us we can do. Now, if they didn't have the quantum entanglement, they wouldn't have been able to do this. if they don't have a quantum channel and they have no shared quantum entanglement, there just isn't a way for Alice to send that qubit to Bob. They can communicate classically, sure, but Alice doesn't know the state of the qubit. She wants Bob to measure it. Well, let's say maybe she can measure it, but even if she can, the point is she doesn't know the state of the qubit. So maybe she does measure it. And then she tells Bob the measurement outcome, and then Bob can use that information about the measurement outcome to try to reconstruct the state. But if she doesn't know the state of the qubit in advance, she doesn't know a way of doing a measurement that won't disturb it. And so typically when she measures it or handles it in some way, she's going to change the state of the qubit, and then there isn't going to be any way to convey the state to Bob, okay? So I got to convince you this really works. This is the teleportation protocol. I told you what it is. Alice has a qubit. She wants to send it to Bob. They have a shared entangled pair. Alice does Bell measurement on her half of the entangled pair and the qubit that appeared in her laboratory just now. She sends the result of her measurement, the outcome of her Bell measurement to Bob, and then Bob applies one of the Pauli operators to get the qubit back. So we just need to do a calculation to see that it really works. So what we start out with is this shared pair, phi plus, that Alice and Bob have had in their labs for a while, that somebody distributed to them, or maybe they prepared themselves. And now there's this unknown state of a qubit in Alice's lab. I'm calling that qubit system C. I want to distinguish it from Alice's half of the entangled pair A and Bob's half of the entangled pair B. It's some state of a single qubit. Let's say it's a pure state. If it's a mixed state, then we'll just consider, applying our protocol to, well, let's just try to send a pure state, okay? So it can be written as coherent superposition, linear combination of basis state 0 and basis state 1 with complex coefficients A and B. And I've written out what phi plus is, this superposition of 0, 0 and 1, 1. And so let me just expand this out. Now I'm using the notation IJK for the 3 qubits. The first one is system C, the second one system A, the third one system B. And so just expanding this out, phi for system C times phi plus gives me A0, 0, 0 plus A0, 1, 1. And I still have the 1 over square root of 2 here from the normalization of phi plus. And then when I have B, 1 for system C tensored with phi plus, that's B 1, 0, 0 plus B 1, 1, 1 in my notation. But now I want to rewrite that in terms of the Bell basis for C and A, because Alice is going to perform her Bell measurement on system C and A. So, well, I can do the algebra this way. Let's look at this state 0, 0, 0. Well, 0, 0, 0, that's just the uniform superposition of phi plus and phi minus, except there's an extra 1 over square root of 2 to get the normalization right. So if I combine together the 1 over square root of 2 and the normalization of phi plus, and then another 1 over square root of 2, because 0, 0 is 1 over square root of 2, phi plus plus phi minus, then I get a 1/2 in front. And so A0, 0 becomes A phi plus plus phi minus for C and A, tensored with 0 for B. And then for a 0, 1, well, I can write that as psi plus plus psi minus times 1 over square root of 2. So that's this term. So it becomes A psi plus plus psi minus times 1 for Bob's system. And then for 1, 0, well, I can take that to be the difference between psi plus and psi minus. So that becomes B times psi plus minus psi minus 0 for system B. And then finally, 1, 1, I can take as the difference of phi plus and phi minus times 1 over square root of 2. And that's going to then be tensored with 1 for system B. And now let's collect the terms together corresponding to each one of the 4 Bell states shared by C and A, the systems that Alice is going to perform her Bell measurement on. So I have to combine together A phi plus 0 plus B phi plus 1. That gives me this term. C and A share phi plus, and then I have A0 plus B1 for system B. And the 2 psi plus terms are this one and this one. So that's going to give me A psi plus times 1 for system B. So that's this psi plus times A1 plus, then I also have psi plus, where is it? Here it is. B psi plus 0 for system B, and that's this plus B0 psi plus term here. And then I have the 2 psi minus terms, this one and this one. So the first one was going to give me psi minus for CA, A times 1 for system B, but then minus B times 0 for system C, system B. So that's A1 minus B0 here. And then I have the 2 phi minus terms, this one and this one. That gives me phi minus for C and A0 for system B minus B1 for system B. So let's just clean this up a little. Let's just clean this up a little bit.
Okay, I found this on the web for persistent B minus B1. Check it out.
There's Siri again going, listening in. I got to do something about that. So if we have phi plus for C and A, this is just psi, the original state, A0 plus B1 in system B. If it's psi plus for C and A, well, this is the result of applying X to psi, because you see that it became, the 0 became a 1 and the 1 became a 0. So it's just a bit flip applied to psi. So I'm writing that as X times psi for system B. If it's psi minus, then this is up to a phase. It's just Y applied to psi, because instead of A0 plus B1, I've got A1 minus B0. Okay, that flipped the bit and also changed the relative phase of the basis states. And when it's phi minus, I have A0 minus B1. That's just the same as applying Z to psi for system B. And so now I've just rewritten the state, which is psi, the qubit Alice wants to send, phi plus the shared entanglement. I've rewritten it in terms of the Bell basis for C and A. And now if we imagine performing the Bell measurement for C and A, we'll notice that these 4 terms in the sum all occur with the coefficient 1/2. So that means that each one of the 4 outcomes of the Bell measurement are equally likely. They all occur with probability equal to the square of this amplitude. They all occur with probability 1/4. So Alice does her measurement, gets one of the 4 possibilities for the Bell basis, phi plus, psi minus, and phi minus. They're all equally likely. And then tells Bob which outcome she got. When Bob knows the outcome, he applies nothing. He applies the identity if Alice's result was phi plus, applies X if her result was psi plus, applies Y if her result was psi minus, and applies Z if her result was phi minus. So you can see, conditioned on Alice's measurement outcome, remember X squared, Y squared, and Z squared are all equal to the identity. That operation applied by Bob just undoes this Pauli operator that had been applied to psi. And so Bob recovers psi, exactly the state that appeared in Bob's lab today. Now, before Alice sends a message to Bob, before he receives that message, Bob doesn't know what he has. And in fact, if he were to measure his qubit, well, it would just be described, it's half of a maximally entangled state. And if you know, it's just density operator is 1/2 the identity. And that doesn't tell him anything about the quantum state that Alice is trying to send to him. Once he has the message, then the purity of the state is restored. With the knowledge of the outcome of Alice's Bell measurement, Bob knows that he doesn't know exactly what he has, but he knows that he has to apply one of these 4 operations, I, X, Y, and Z, in order to get the state that Alice was trying to send him. Neither Alice nor Bob knows anything about what psi is, okay? If Bob hasn't measured it yet, he doesn't know anything about it. All he knows is that he has it, okay? Now, it's good that they don't know anything about it because, as you know, if you acquire information about a quantum state, if it's an unknown state, you're going to damage it. You're going to cause some disturbance. And that hasn't happened here. Alice doesn't know what psi is. Bob doesn't know what psi is. But the protocol has conveyed the state psi perfectly from Alice's lab to Bob's lab. Now, remember, we talked about how you can't clone unknown quantum states. I think I mentioned that back in the first lecture. Well, this looks a little suspicious because there was a qubit in Alice's lab and suddenly it's in Bob's lab as well. Does that sound like cloning? Maybe it does, but it's not, because Alice had to destroy her copy of the qubit when she did her Bell measurement. She can't get it back anymore in her lab. All she can do is send the measurement outcome over to Bob. And now, once Bob knows that classical message, Bob's got the state. No, it's never the case that a single copy of the state becomes 2 copies at the same time. In order for the state psi to magically appear in Bob's lab, it had to be destroyed in Alice's lab, okay? And there had to be time for the classical message to travel from Alice to Bob before Bob could recover it. So if you want to look at it from the point of view of, you know, faster than light communication, the state doesn't travel faster than light. It doesn't appear in Bob's lab until Bob can receive that classical message. So the reappearance of psi in Bob's lab, as the relativists say, is in the forward light cone of the event in which Alice does her Bell measurement. And there isn't any time, any slice through space-time where 2 copies of the state are both there at once. Now those 2 classical bits, what if that nosy Eve is listening in again and learns what those 2 classical bits are? Is she going to know something about this secret quantum state psi that Alice is sending to Bob? Well, no, she's not going to know anything about it because those 2 classical bits were uniformly random. All 4 possible outcomes of the Bell measurement were equally likely. One of them occurred. That would be the case no matter what the state is. So those uniformly random bits don't tell us anything about the quantum state. So how is it? How is this working? How is it that we're able to send a quantum state from Pasadena to Waterloo by just sending 2 classical bits? I mean, there's something in a way surprising about it, a little bit miraculous. Is it the classical bits that are somehow sending the information from Alice to Bob? Well, that can't really be it, right? Because they're just 2 uniformly random bits and they're not telling us anything about the quantum state on their own. The quantum entanglement is essential. It wouldn't have worked without it, but it's not enough by itself, not enough without that classical communication. It's the 2 together that really do it. And remember that entanglement that Alice and Bob share, which they use in the protocol, that doesn't have anything to do with the quantum state we're trying to send. They could have prepared that entangled pair last year, knowing they might need it someday. In fact, that's exactly what happened. They did do it last year. And now that qubit shows up today, and of course that entangled pair doesn't know anything about what qubit is going to show up today. So The entanglement by itself isn't any good. If Bob just has half of the entanglement, he just has a maximally mixed state. That's not a very precious commodity. It's the two together, the shared entanglement and the classical communication, that make this teleportation possible. Now, I keep saying nobody knows what psi is. Nobody knows what psi is. So how are we to say that the teleportation really worked? Is there a way to verify it, to validate it? Well, in principle, we could. It could be that there's another party, Charlie, who prepares psi, and he does know how he did it. He knows how he prepared it. He knows what the state is. And so he gives it to Alice. He doesn't tell Alice what the state is, anything about how he prepared it. But Alice and Bob carry out this protocol. And then Bob goes over to visit, Charlie goes over to visit Bob's lab. And when he gets there, he can perform a measurement which projects onto two states of the qubit, either psi, the state that Charlie knows he prepared, or the orthogonal complement of psi, a state orthogonal to psi. So if the teleportation worked perfectly, then when he does that measurement, he'll get the outcome psi every time. He'll never get the outcome psi perp. So Alice and Bob can try this protocol 1,000 times. Each time Charlie gives them a state, he might as well, just to make it hard on them, prepare a different state every time. But he should always successfully verify that the state is psi. It'll never be psi perp. And after he's done that 1,000 times, we're pretty confident that this teleportation is a real thing, and the state is really being transferred with very high fidelity.
Hello, what can I do for you?
Okay, so now I want to look at this in a somewhat more general way. Just by going to higher dimensions, I think this is helpful for understanding how this teleportation works, and it gives us a way of generalizing it, which is sometimes useful. So let's talk about this a little bit. Now I'm going to suppose that Alice and Bob have n-dimensional Hilbert spaces, and they share a maximally entangled state of their n-dimensional systems. So this is the analog of phi plus, which we talked about for qubits. I'm just calling it capital phi. It's this standard maximally entangled state, the same one we talked about when we were discussing the duality between states and channels, the Choi-Yamiokowski isomorphism. I choose a basis for Alice's system, a basis for Bob's, and the state is just the uniform superposition of I tensor I summed over the n basis states. And now there's something that's kind of useful to notice. Let's suppose that Alice applies some unitary transformation to this maximally entangled state, which I called capital phi. So I'm going to write this unitary as an n by n unitary matrix. Acting on the basis element I, it'll give me the sum over j of uji. And so the state capital phi, when Alice applies u, becomes this state, the normalization factor times the sum of j, matrix element u sub ji, tensored I for Bob's system. And well, here I've just taken u and moved it over and taken its transpose. So I wrote uji as the transpose of uij. But you see, that's the same thing. If I now think of summing over I, that's the same thing as if I had applied U transpose to the basis state J. And so this is the same thing as the identity for Alice tensored with U transpose for Bob, acting on the maximally entangled state capital phi. So in other words, whatever unitary transformation Alice applies to the state, the equivalent change in the maximally entangled state could have been achieved by Bob applying a unitary to his half of the state. But if Alice is applying U, then Bob has to apply U transpose in order to change the maximally entangled state in the same way. And likewise, if they both apply unitaries, let's say Alice applies U and Bob applies V, well, I can think of that this way. It's U tensor identity times identity tensor V. And in the case of the U tensor identity, I can replace that by an identity tensor U transpose and then apply identity tensor V. And so the result is the product of those two will be identity tensor V U transpose. So having Alice apply a unitary and Bob apply a unitary, that's can be accomplished, the same thing can be accomplished by just having Bob apply the appropriate unitary. And likewise, we can get the state that results from Alice applying U and Bob applying V by a transformation, a unitary that acts only on Alice's side. So now I would take identity tensor V and I would write that as V transpose tensor A, and then apply U tensor identity, and I would get U V transpose tensor I. Or if you like, I can just use what I observed here and take U V transpose applied by Alice, tensor I, and then take the transpose of this, which is V U transpose applied by Bob, and that gives me the same effect. So in fact, any maximally entangled state can be obtained from any other by applying a unitary either on Alice's side or on Bob's side. In the case of maximally entangled states, that's the case in which the Schmidt basis is ambiguous. I can choose any orthonormal basis I want for Alice or for Bob as the Schmidt basis. But once I fix the orthonormal basis for Alice, if I have some particular state, then that's going to lock in the corresponding basis for Bob, which is related to it by the Schmidt form. But for a general entangled state, Alice has some orthonormal basis and Bob has one, and they're perfectly correlated with one another. And all those states are related by applying unitaries on Alice's side and Bob's side. But all I'm saying is they don't both have to apply unitaries. It's enough for one or the other to do it to get any entangled state I want. So any maximally entangled state of these two n-dimensional systems can be written as our standard state, called capital phi, for some particular choice of bases for Alice and Bob, and then unitary on Alice's side applied to that state. And just as a notation, I'm going to call that capital phi of U, the result of taking capital phi and applying U on Alice's side to get a different maximally entangled state. And all the maximally entangled states can be written in that form. So now I want to think about a protocol like this one that we talked about before for qubits, but where now there's a measurement in a maximally entangled basis performed by in Alice's lab. So now there's some n-dimensional system coming into Alice's lab, and there's a state like capital phi, or in general U tensored capital phi, a maximally entangled state shared by Alice and Bob. And so in order to figure out what's going on there, I want to evaluate this quantity. This bra associated with phi for CA, I can think of, as usual, as a linear operator. And when it acts on a state for systems A and B, the result is an operator that takes system C to system B. And we can see how that works just by calculating it out explicitly. So I write down the expression for the ket phi as a sum over j times 1 over square root of n, and for the bra phi as the sum over I, factor of 1 over square root of n. So I get 1 over n from those two factors of 1 over square root of n. And now here you see I have a ket for system A and a corresponding bra for system A, but these are an orthonormal basis, so that's an inner product, which is going to collapse to only the terms with I equals j. And so now the only terms around are the ones in which I have the same index for the basis state for C and for B. And so I'm going to take this ket for No, that's a bra. I'm going to take this bra for system C and move it here over to the right. And the ket for system B and move it over here to the left. And so what we have here, up to the normalization with this factor of 1 over n, looks like an identity operator, but I'm not going to call it the identity operator because it's really mapping one system to another. It's not the identity acting on, say, system B. It's an operator that takes states of system C to states of system B. So I'm going to call it a transfer operator. But it is a transfer operator that takes a state for system C and transfers it to the identical state for system B. Now, we got to be a little bit careful here. I have the same state for system C and system B. It's implicit, at least, that there's some shared reference. So I know how the, if I say basis state I for system B, I have to have some convention, some means of saying what is the basis state for the other system that I'm going to identify with that. And that's what I mean by a reference frame or some kind of shared reference between the two systems. That was already kind of implicit when I wrote down our expression for phi. I said basis state I for B and basis state, or, for one system, basis state I perfectly correlated with basis state I for the other system. And so if you can think of phi as defining that reference, which basis state for the one system I associate with the basis state for the other. And this is actually important to keep in mind if we want to do an experiment to check that if I send a qubit from Alice to Bob, the qubit that Bob gets is really the qubit that Alice sent. What does that even mean? I have to have some way of comparing these two Hilbert spaces. That's what the reference frame does. Alice could say, okay, I'm going to send a particular linear combination of basis state 0 and basis state 1, A0 plus B1. Now Bob gets this qubit, but how is he supposed to know what basis states in his system correspond to what Alice calls 0 and Alice calls 1? They have to have some way of figuring that out. So if they're good experimentalists, they will have established a shared reference somehow, maybe by using, the phase of lasers in their labs or something. So, or maybe they have very precise clocks they were able to synchronize or something. So we're sort of taking it for granted that they have some way of solving that problem when we say that this transfer operator takes psi for system C and maps it to psi for system B. That is, for some appropriate choice of shared reference between the two systems. Okay, so now I want to look at this, this higher dimensional version of teleportation. Some state for system C has arrived in Alice's lab for this n-dimensional system. And Alice is going to perform measurements which project onto a maximally entangled basis, okay? So one of those basis states could be this state that I've been calling capital phi. Alice and Bob have prepared some time ago a maximally entangled state of systems A and B, which they share, and they're going to make use of that in the protocol. And now I just told you about this transfer operator, which comes from applying this bra, capital phi for CA, to the ket, capital phi for AB. But now for the scenario that I now want to consider, a teleportation protocol, I want to consider the, well, actually, I'll be a little more general than we were before. The initial entangled state that Alice and Bob shared isn't necessarily capital phi. It could be any other maximally entangled state. So I can get any such maximally entangled state shared by Alice and Bob by applying a unitary on one side, could be on Alice's side or on Bob's. Here I've chosen to apply V on Bob's side to get the maximally entangled state of interest for A and B. And according to my conventions, which is, I label the state according to the unitary applied on Alice's side, this is capital phi of V transpose, because applying V on Bob's side to capital phi, that's equivalent to applying V transpose on Alice's side. And now when they perform their Bell measurement, they're going to project out a particular maximally entangled state. What maximally entangled state is it? Well, I know whatever it is, I can write it in the form of a unitary applied to system C, tensored identity for system A, acting on our standard maximally entangled state, capital phi, for CA. So now I want to consider, to understand how information is flowing through this diagram, what happens when the projection corresponding to the outcome of the Bell measurement is not projecting onto the state capital phi for CA, but the state that I called capital phi of U. And the initial prepared entangled state of Alice and Bob is not necessarily capital phi, but some other maximally entangled state, which I've called capital phi of V transpose. But now, if you look at what we already know here, that if I do have capital phi for CA and capital phi for AB, I just get the transfer operator. And you see that this state can be obtained by just applying V on Bob's side to capital phi. And now when I take the Hermitian conjugate of phi of U for CA, this U becomes a U inverse or a U dagger. So I'm going to get the same transfer operator we had before, except there's going to be an extra U inverse, which is acting on system C. And there's going to be, and that's coming from the fact that the Bell measurement didn't project onto capital phi, rather projected onto phi of U. That's where the U inverse came from on system C. But furthermore, the initial maximally entangled state for AB wasn't capital phi, it was capital phi of a V transpose. And that means there's an extra V now acting on system B, which is this V. So I could think about it this way, that the inverse of U is applied to system C, then C is transferred to B, and then the unitary V sub B is applied to system B. But because of the way our transfer operator is defined, if I apply a unitary to system C and then I do the transfer, that's the same thing as applying the transfer first and then applying that unitary, because the transfer operator has the property that it's exactly the same state for system B as for system C when the transfer operator takes the state from C to B. So I could just as well say that we do the transfer first, and then we apply the product of V and U inverse after the system has been transferred to B. Okay, so now I'm trying to capture that in the diagram here, that if we actually did Bell measurement and the outcome of the measurement were not capital phi, but rather phi of U, it's as though we applied U inverse first to the incoming state, which Alice is trying to send over to Bob, then did Bell measurement and got the outcome capital phi. It's exactly the same thing. And if the maximally entangled state that was pre-shared by Alice and Bob was not capital phi, but rather what I called capital phi of V transpose, well, that's the same as if it were capital phi, but then at some later time, V were applied to system B. Okay, so the upshot of all that is, and that's what this equation says, is that when the result of the Bell measurement is phi of u, and if the initial shared entanglement of A and B were the state phi of V transpose, then what is going to appear in Bob's lab is not the perfectly transferred state C to B, it's going to be modified by this extra unitary V times U inverse. But if V is equal to U, then it's going to be a perfect transfer, just like we had in the case where the result of the Bell measurement was phi and the initial state was phi, okay? So you could look at it this way, that whenever you do that Bell measurement in this type of protocol, you get some outcome which is a maximally entangled state. And if, let's say, the initial shared entanglement between Alice and Bob were the state capital phi, and the result of the Bell measurement were also capital phi, then we get a perfect transfer. We just get this transfer operator, and the state psi that started out in C would be mapped to the same state for system B in Bob's lab. In fact, we got some other result of the Bell measurement, not the one we wanted. And we say to ourselves, oh, well, gee, if only I had prepared the right maximally entangled state in the first place for Alice and Bob, then that Bell measurement would correspond to the one that would give me perfect transfer. It's just that I didn't prepare the right entangled state to begin with, so it didn't quite work. But you see, it's not too late to fix it, because if you didn't prepare, you didn't have the foresight to know what maximally entangled state for Alice and Bob you were going to need for the Bell measurement applied to C and A to give you the perfect transfer, you can fix the state that Alice and Bob share. It's not too late. And all you have to do is apply a unitary on Bob's side. And it's just the same as if you had had a different shared entangled state of Alice and Bob to begin with. And now the protocol worked perfectly, and you will get a perfect transfer, okay? So another way of saying it is that if you do the Bell measurement and you get a particular maximally entangled state, which is labeled by a U, and if the initial entangled state shared by Alice and Bob was a maximally entangled state labeled by V, and now Alice and Bob, in particular Bob, knows what that initial entangled state was, so he knows V. And once Alice tells him what the outcome of the Bell measurement is, he also knows U. Well, now he can go ahead and apply V inverse and then U, and he's going to get psi. So that's, from this point of view, the way quantum teleportation works. What do I mean by this point of view? I mean the point of view that you would get perfect transfer if Alice and Bob had known in advance to prepare the right entangled state, given what the Bell measurement turned out to be. But even if they didn't prepare the right entangled state to be shared between Alice and Bob to begin with, you can fix it, because all you need to do is apply a unitary on Bob's side, and it's not too late to do that, even if Alice has already done her Bell measurement on CNA. So there's kind of a nice way of looking at the way information is flowing through this diagram. In fact, I did kind of a sneaky thing without comment until now. I have this arrow pointing backward in time. That isn't what I had done before. I had said, okay, there's some state, capital phi, which someone nicely prepared. Maybe it was Donald, and he sent one half over to Alice, and he sent the other half over to Bob. But there's another kind of fanciful way of thinking about what's going on here, that information is flowing from Charlie's preparation of the state psi forward in time to the Bell measurement performed in Alice's lab on CNA, and then it goes backward in time back to the preparation of the entangled state of A and B, and then forward in time again to Bob's lab. And that helps one to understand the order of operations here, that you can think of the U inverse, which is associated with the outcome of this Bell measurement, as something that was applied early on to the state prepared by Charlie. And then later on, V was applied to Bob's half of the system. And so if you, think of the state going forward, back, and forward again, the U inverse comes first and the V comes later. And that's why we wind up with first U inverse and then V applied to the state psi. And that's what ends up in Bob's lab. You may or may not like that way of thinking about how the teleportation is working, but it actually can be very helpful for keeping track of where information is going if we had a more complicated network of state preparations and measurements. Now, let me mention an application of this kind of scenario. Let's suppose that I would like to apply a particular unitary transformation to a state psi. I don't know what the state psi is, as usual. It's just some state, let's say, of a qubit. But I do know I want to apply a particular unitary transformation to it. If I had just the right hardware in my lab, I'd be able to do that. But I don't have that hardware. It turns out to be too hard for me to do. And so I'd like to find some indirect way that still works of applying V to that unknown state psi. Well, grant me a couple of things. Let's suppose I do have the hardware to make a, I guess that was supposed to be a capital Phi, sorry about that, to make a maximally entangled state, which is labeled by V. In other words, the result of applying identity tensor V to the state phi tilde. Well, maybe I don't have that hardware myself, but maybe I asked a vendor to ship me some copies of capital Phi of V transpose. So I have some of those around. Or maybe I was able to make them myself. And I also know how to do Bell measurement and to project onto some particular basis. If it's a single qubit, it could be the same Bell basis we talked about before, associated with the 4 poly operators, identity X, Y, and Z. And so now I can do this teleportation protocol myself. I know how to make the maximally entangled state. I know how to do Bell measurement. And then the result will be, because I started out with the entangled state labeled by V, and the result of my Bell measurement was the maximally entangled state labeled by U, what I'll wind up with after all that in my lab is the result of applying VU inverse to psi. And now to get what I want, which is to apply V to psi, I can apply V inverse and then U and then V. So the V inverse cancels the V, the U cancels the U inverse, and I wind up with just V applied to psi. So you might think this is kind of silly because I'm taking it for granted that I can apply VU, V inverse, but I claim it's hard to apply V. But this is a real thing that happens in quantum error correction and fault-tolerant quantum computing, that in quantum error correction, I encode the data in some sophisticated, highly entangled form, and I can't apply just any old gate I want to the quantum information when it's encoded in a certain way. There are only certain gates that are easy to apply. The other ones are too hard to do, so that I'll probably wind up damaging the information and defeating the purpose of the code. Now you see, it kind of makes sense that there are only certain discrete unitary transformations that you can apply to the encode, that you could apply to the encoded data. Because if you could apply any unitary you want, Who's to say that you applied exactly the right unitary? If you wanted to rotate the qubit on the Bloch sphere by 90 degrees, you might wind up rotating it by 91 degrees instead, and it would still live in the code. It would still be protected by the quantum error correction. And how would I know that I had applied the wrong unitary? Well, the way it actually works is there are only discrete transformations that you can apply in a way that preserves the nice structure of the code. And some of those you can do and some you can't do. And the ones that you can do are typically not enough to operate a universal quantum computer, so you have to find some way of working around that. And a scenario like this is exactly what arises, that although I might not be able to apply V, I might be able to apply VU, V inverse. Now there's another thing that might seem kind of silly about this, which is I took it for granted that I could apply, or I could create the maximally entangled state, which results from V being applied on one side to phi. And if I don't have the hardware to make V, why should I assume I can do that? Well, actually, they see there's a difference between applying a unitary transformation to an unknown state and trying to prepare a known state. Now, I know what unitary I'm trying to apply. I know it's V, and I know what capital phi is. So I know I'm trying to create a particular state, I tensor V applied to capital phi. And if I have a way of checking that I've done it right, sometimes I might fail, and then I can throw out the failed attempts. But when I do it right, I can then use that entangled state with the teleportation protocol to achieve the effect of applying V to the input state psi. So the key thing is that even if my hardware isn't reliable enough so that I'm willing to take the risk of applying V to the unknown state, because if I do that wrong, there won't be any way to recover because I don't know what the state was supposed to be. I don't want to take that risk, but I am willing to take a shot at preparing some known state if there's a way of checking that I did it right, of validating my quantum software, which I'm going to use for this protocol. So you can think of this quantum software as something I either make myself or which I buy from the vendor, this maximally entangled state labeled by V. And every time I want to apply V, I consume some of this software. I use it up, just like in quantum teleportation. Every time you want to send a qubit, you're going to consume an E-bit of entanglement, or every time you want to do superdense coding, you're going to consume an E-bit of entanglement, because without consuming entanglement, you can't get the job done. I'm going to need if I want to continue applying V, I'm going to need a continuing supply of the quantum software. I'm going to have to keep replenishing my supply of the entangled state that I use to carry out this protocol to apply V to the unknown state. Now, teleportation is a lot like that too, because if I'm trying to teleport a quantum state, the type of scenario I described is we don't have any quantum channel at all that connects Alice to Bob. A somewhat more realistic setting might be that we have a quantum channel, but we don't trust it because it's too noisy. And I'd like to be able to send a quantum state from Alice to Bob, but I don't want to just shoot the state through the channel because I'm afraid that it'll be damaged, and by the time it gets to Bob's lab, it will be irreparably damaged. I won't be able to get it back again. What I can try to do instead is to establish an entangled state shared by Alice and Bob through the quantum channel. And I might not succeed every time, but if I have some way of checking when I get the maximally entangled state and when I don't, if I can somehow, validate that it worked, then I'll be pretty happy because I can create a supply of entangled pairs and I can use them to teleport to get quantum states to go from one place to another. There are lots of reasons why I might want to send quantum states from one place to another. One might just be that I want to scale up a quantum computer. The truth is that with today's quantum hardware, there's a limit at present to how many working qubits you can have in a given processor. For example, it might be an ion trap, and the state of the art is you can put maybe 32 ions in a trap and control them very well, but 64 is hard. 128 is beyond what anybody has done. So if I want to scale up a quantum computer, perhaps what I'm going to prefer to do, instead of putting lots and lots of ions in a single trap, is to multiplex the traps. So I'll have a lot of traps, each one maybe with 32 ions or some, relatively modest number, but I'd like to have thousands of qubits. And so I have to somehow wire those different processors together. And a way that you might do it is by using quantum teleportation from one trap to another. The way you might establish entanglement between the traps is by sending entangled pairs of photons. We're pretty good at making entangled pairs of photons, and we could try to shoot one of those at ion trap A and another one at ion trap B. And if it's heralded that the qubit was absorbed in trap A and in trap B, that I know when it happens, even if it doesn't happen that often, if I know when it happens, then I can have some shared entanglement between the two traps. And then I can convey quantum information from trap A to trap B. And now I can treat my assemblage of processors, all my different traps, as one unified system, because there's quantum communication between the different processor. Whereas if I tried to send qubits directly from trap A to trap B, say by taking an ion and carefully shuttling it over from trap A to trap B, maybe that's less reliable, because in some cases the quantum information will be lost, and then I can't undo the operation. But if I have a way of checking that I have shared entanglement and only teleport when I think the entanglement is good, I can do a better job. And another reason why I might want to send quantum information is in cryptographic applications. I'm not going to say a whole lot about that this term. I mentioned it in the first lecture, that there are ways of doing private communication. We're actually pretty close to being able to discuss that, but I want to move on to start talking about computation next time. But at any rate, one reason why you might want to send quantum signals over long distances is for quantum cryptography, to do private communication with quantum states. And the state of the art now is that, well, you usually send photons. Those are the qubits which travel the best. If you want to send them over distances of kilometers, we're pretty good at that. To send photons, you usually do it either by sending them through optical fiber, the same kind of optical fiber that we use for telecommunication these days, or you can send them through free space. And that's been done fairly successfully. It's even possible to send photonic qubits between a station on the ground and a satellite in low Earth orbit, or the other way around. But if you want to send quantum communication, if you want to send qubits over long distances, that's pretty hard, because there's a lot of loss in optical fiber. The quality of the fiber is such that if you try to send a photon 100 kilometers through fiber, choosing the wavelength of the photon to be the best possible one with the lowest loss, for every 50 photons you send through 100 kilometers of fiber, only one gets through. And if you tried to send them 1,000 kilometers, the fraction that would get through is 1 over 50 to the 10th power, because it's 10 times as far, about 10 to the minus 17, so hardly any. If you like to be able to send a qubit from one point on Earth to another point thousands of kilometers away, then you have to figure out some way of mitigating those limitations in direct quantum communication. And a possible way to do it is to use teleportation. That's probably is how we'll do it. Again, we make use of the idea that we establish entanglement between 2 points, and we can check whether the entanglement was successfully distributed or not. Then we can use it for teleportation. And the way you would get to such long distances is through a kind of hierarchical procedure where you'd establish entanglement between point A and point B, which are maybe tens of kilometers apart. But then you could, kind of leap to the next level of the hierarchy, and through teleportation, send entanglement over longer distances, and so on, and eventually achieve communication on a global scale. That hasn't been done yet. Some of the technology still needs to be developed. In particular, we would like to have a quantum memory to be able to hold on to the qubits for a while in order to carry out that type of protocol. Okay, well, that was just a little information for your edification about why quantum teleportation might actually be useful for quantum technology. And I think I will leave it at that for now. And next time we'll start a new topic. Now, I know a lot of you have backgrounds in computer science, in particular in complexity and algorithms, but some of you do not, and I don't want to assume that you do. So I will try to convey the things that we would like to know about complexity theory without assuming any prior background. And I guess we'll start doing that next time. So meanwhile, good to see you again. I know you're out there still paying rapt attention to the things that I'm saying. I appreciate that. Thank you for your attention. And until next time, be well, have fun. See you soon.